Thanks for having me back. It's been a little while, I think since the before times, so thank you for inviting me. It's always fun to come and talk about my job. And what's really amazing is I get to tell people that what I do, there aren't a whole lot of actual jobs in the country that involve doing the combination of public outreach, education, and now research that we do with the observatory. So the Doane Observatory was originally conceived of in the 50s or so, and staff at the Adler had produced a mirror for a telescope before they even knew where they were going to put it. There were original ideas for putting the Doane Observatory on the roof of the Adler. If you think to yourself of what the roof of the Adler looks like, there is a big giant dome sitting right next to the flat part of the roof. Yeah, that I don't think would have gone very well if they had done that. And you know, a structure for a telescope on top of a building with an HVAC system. Yeah, you can probably imagine it would not have been a great idea. So there were ideas afoot to build a separate observatory. And so now they needed someone to fund it. And lo and behold, there was a family of the last name of Doane, D-O-A-N-E. Everybody thinks I'm saying the word dome, but it is Doane. And the family was looking for a way to support the museum community in Chicago with some sort of philanthropic gift in memory of their parents, Ralph and Lillian Doane. And so Ralph was originally from Chicago. Lillian was from my hometown of Minooka. And he had made a tidy little fortune. He had purchased the patent rights to essentially mass mailing technology, and then he sold that to Xerox. And so if you want to know who to blame for mass mailings that you get, you might be able to blame Ralph Doane for some of that. But they made a little bit of money, and Ralph and Lillian both passed away in the early 70s. And so the family then was looking for some way to remember them, honor them. And so they approached the Adler and they said, "So what do you got?" And we said, well, not we, I wasn't there at the time. They said, "Well, we have this idea of building an observatory." They went, "All right, let's do it." So Ralph and Lillian's legacy started to be built. And if you have not been to the Adler, I'm talking about the little building that is directly to the east. Somewhat a kind of brutalist architecture, lots of concrete, so much concrete in this building, so much concrete and rebar that we do not have to have the telescope pier separate from the rest of the building. It is incorporated in the building because it's not moving. And so you can slam every door in that building as much as you want. It will not translate to the telescope, which is actually really great. But the building, they started building it in the early 1977 or so. And you can tell by the vehicles that are there. And yes, that is the road that used to go behind the Adler. Yes, we used to get free parking back there. Not anymore by any stretch, but the building was poured, and then the observatory itself opened August 5th of 1977. And the first telescope that was in there was the one that with the mirrors that were built, the whole telescope actually was built at the Adler. So as you probably remember, we used to have the mirror making workshop. Yes, I am going to bring back the mirror making workshop in some way. I've already been talking with Tony Harris, who many of you know, from Chicago Astronomical Society, Mark Christensen from the Fox Valley Astronomical Society, and several others. There are definitely a lot more interesting ways of making telescope mirrors these days that don't always require you to stand there and grind the mirror over and over and switch and turn and over and over. There are actually other ways to do it that in some cases involve, and I'm going to digress for a second, you take a spherical mirror, you attach a puller on the back and you pull it into a parabolic shape. It takes about 15 minutes. And so I can't claim that we'll ever get that quick with making telescope mirrors, but yes, this is going to come back. And if I have anything to do with it, so don't worry, I've got you. Back to our story. The telescope was built at the Adler. In total, everything, and they added the ability to put a TV camera on the back. And unfortunately, the mount itself was not quite as sturdy as they needed it to be. The telescope did suffer from a bit of shaking. So they knew that it wasn't going to be a telescope they wanted to keep in there forever. But it did definitely serve them well. The observatory was extremely popular, so much so that they installed television screens. So if you ever go into the observatory and there are these big metal cabinets that are on the exterior walkway on the interior of the observatory, big metal cabinets, they installed TV screens in there so that video cameras attached to the telescope could show people what the telescope is looking at on the TV screens, because in many cases, this observatory was a victim of its own success pretty much from the beginning. There were some nights they were getting 2,000, 3,000, upwards of 5,000 people coming to an evening observing. And so that's an awful lot of people to try to get eyeballs up to a telescope. So in order to alleviate that, they stuck the TV camera on at times. And one of my favorite pictures, which is kind of interesting if you take a look, this is a lunar eclipse event, July 1981. You can see all the people, and they're looking at cathode ray tube TV screens that are inside these cabinets. Not one person in this crowd is looking up at the moon. If you think people were fascinated by screens now, they were back then too. So that is not actually an ideal situation where you want people to be looking up at the lunar eclipse that's in the sky. So they needed to do a little bit better than that, but it was really popular right from the beginning. So lots of people through. The original telescope was replaced in 1987, and the original telescope was a 16-inch reflector. The new telescope was a 20-inch reflector, and it was produced by DFM Engineering. So Dr. Frank Malsheimer, his company created this telescope. And the telescope, the Adler was able to pay for the telescope itself from money that they earned from all the people who came to see all the events related to Halley's Comet in 1985 and 86. So enough to pay for a research grade telescope. So you can see a lot of the original equipment that was in there. And if you go in there today, it still looks remarkably like this, especially the architecture. The computers have definitely improved. But one of the problems that was noted always from the beginning was just the inability to get lots and lots and lots of people through easily, because there was one way in and the same way out in order to get into the room where the telescope was. So it's a bit of a bottleneck. Well, enter a great grant from the state of Illinois in 2014 that allowed us to basically build out what the space was underneath the telescope room. It was basically just kind of a mud pit, gravel pit, and so there was no room in there. You could think of it kind of like a crawl space sort of space. So what they did was they brought in 30 truckloads of gravel and built up the level of the floor to the level of the ground, and built the multi-purpose room that we now have in the lower level of the observatory. So the multi-purpose room we can use for get-togethers, public programs. It can fit somewhere around 15 or 20 people. And what you can't see right back here is there's a cabinet in the back. We can run the telescope from the multi-purpose room, and the telescope is upstairs in the telescope room. So here is a little bit better view of that space in the back. So it's sort of our sort of research space. So the multi-purpose room, I said, has been around since 2014, and in October of 2019, we took out the DFM telescope and replaced it with a 24-inch PlaneWave telescope, and we love our PlaneWave. The PlaneWave went in January of 2020. And then the Adler closed for 1 week shy of 2 years in March of 2020. So we were closed to the public from March of 2020 to March of 2022. Because of the pandemic, we weren't easily able to get downtown to be able to use the telescope all that often. At the time, because we were initially under lockdown conditions, but then under very, very strict capacity limits, I had to arrange nights about 2 months in advance to be able to go down and attempt to use the telescope. Well, as you know, it's hard to predict the weather 2 days in advance, let alone 2 months. And so there were only maybe about 5 or 6 times we were able to get in and actually use the telescope while we were closed. But we did get a chance to try it out. And if you've never used a PlaneWave telescope, they are spectacular. I cannot say enough about this equipment. It's amazing. It's rock solid. The software is amazing, really easy to use. This telescope is practically silent, and it's just an incredible piece of equipment. One of the things you may notice off here to the right is that is a 6-inch, Takahashi 4-inch Takahashi telescope. And that's a refractor. We initially thought we were going to use it as a finder, but the PlaneWave is so good, we don't need a finder scope on this thing. So we took that off and we use it just on a regular mount. So we're able to use it, you'll see early pictures of it included, but we actually had to take that off and we'll use it separately. The other problem was this telescope is big enough and the mount is big enough, and when you add on a telescope to the other side of it, the opening in the roof isn't big enough to accommodate looking through both telescopes at the same time. So we, for that other reason, took that so-called refractor off, or so-called finder scope off. Anyway, it's an absolutely beautiful piece of equipment. Some parts of it are 3D printed. The trusses are 3D printed. Actually, if you get a PlaneWave today, our baffles, our light baffles on the interior are metal, but they 3D print those pieces as well. So overall, the telescope itself, a truss tube telescope, only weighs about 250 pounds. You can get maybe 3 of us together and we can lift this thing up. It's really not all that heavy, and it moves just absolutely beautifully. So we knew when we installed it that we thought, okay, we may have some capability to be able to do some research with this thing. We want to get people's eyeballs up to it, and that's the main reason for it. But on the nights that we're not open to the public, so we're open every Wednesday night to the public from 4 to 10 p.m. is when the Adler is open, and when it's clear out, the observatory is open after sunset. And so anyone walking by, basically the rule is if you see the door open, come in. And you can come take a look at whatever it is we happen to be looking at. But that's only one night a week. We've got 6 other nights of the week that we could use for other stuff. So we started to think about what kinds of research we could do with a telescope that is sitting on the shores of Lake Michigan next to one of the worst light pollution situations in the entire planet. So what can we do? Well, we have goals. It's good to have goals. Undergrad and high school students will participate in an authentic research program. Basically, we don't necessarily want to keep looking at the same thing over and over and over. We want to actually contribute in some way, if we can. We want to give students hands-on experience with this telescope. Yes, we are slowly building in remote operating capability. We are working on that. But one of the main things we think we have over practically any other research facility is you pretty much at any other research facility don't get your hands on the telescope. And so you want to turn out astronomy students and physics students who know what this is all about. So we want to give them opportunities to work with the equipment directly. We're starting with undergraduate students. And so we had 2 undergrad interns last summer. We've got 2 coming in this summer. And those 2 ladies last summer were fantastic. The 2 ladies we have coming in this summer are absolutely amazing, and I cannot wait to work with them starting in June. But one of the things that we also know is very unique to our program is when we are open on Wednesday nights, they're going to come and interact with the public as well, because one of the questions we get more than just about anything else is, so what research do you guys do with this? The public wants to know. They want to know, what else are we using the telescope for? So we said, all right, we need to sit down and figure out what our telescope is good at. What could we use it for? So authentic research program, hands-on experience, facilitating public observing sessions to give students a chance to see what the public's interested in and give the public a chance to talk with people who are doing an actual research program, some sort of research question or data gathering in some way. So we think it's a win-win situation. But we had to get to know our equipment first. And that's because we were closed for 2 years. We barely knew how to operate the telescope properly. So we needed to characterize what our telescope was good at. So get to know the equipment and the environment. What does the light pollution allow us to actually see? What can we expect? We want to take our sample image sets and then find funding and partners to help support the program. But what is going to be our target, our types of things that we want to look at? Well, things that change in brightness. Those are the most interesting stuff, right? And what can we be good at? Variable stars, supernovae, if they're bright enough, exoplanet transits, believe it or not, asteroid light curves, possibly occultations. We haven't tried that out yet. We have the equipment to do it, but we haven't tried it yet. And watch Jupiter for a couple months and see if it gets hit by stuff. Throw a methane filter on that telescope, video it for 5-6 hours in a night and see what happens. And do that for a couple of months. So there's apparently software out there that can pick out the flashes that happen when asteroids and or comets impact Jupiter's atmosphere. So that's another thing that we might want to do. We've actually been able to do test images and test data sets with a lot of this. And so I'll get to those results in just a second. Now, the first thing we needed to figure out was, how low can we go? What's the dimmest stuff we can see with our telescope? And actually, believe it or not, we can get too bright with our telescope. About around 8th, 9th, 10th magnitude for taking data is actually too bright. That's too bright for us. Those are images that we can take in maybe 5 seconds, maybe 2 seconds. That's actually not good. We need stuff that's actually a little dimmer. But just to give us a sense of scale, Venus is at about -5 magnitude, Jupiter is about -2, Vega is about 0. Human eye can see down to about 6 magnitude, and if you walk up to our telescope and stick your eyeball up to it, given our light pollution situation, you're going to see stuff down to maybe about 10th magnitude, as long as the sky is really dry and it's not very humid at all, and it's really good seeing, and very nice and steady. That's the range of what we can expect without the camera equipment. Now, when you start putting camera equipment on the telescope, we have a ZWO ASI 183mm camera. So it's a monochrome, a grayscale camera, and we put a filter wheel on it. And so it's a ZWO electronic filter wheel. We have a blue wideband filter, a visible wideband filter, which basically centers on the green part of the spectrum, red wideband filter, infrared wideband filter, a methane filter in case we want to stare at Jupiter for a while. In position 6, right here, that is a diffraction grating filter if we want to look at some spectra. Position 7 is a clear filter because if we want to focus the telescope, you don't want to do that with one of the filters when you can hardly see some of the stars. You want to do it with a clear filter, but do it with the same type of filter so that you don't have to change your focus point when you switch to one of the other filters. And then position 8, we currently don't have a filter in there. So with this as our equipment setup, what can we do? Well, this graph shows the accuracy of the data that we get depends on the exposure time and the brightness of the target stars. So we've been able to take images of objects down to about 16th to 18th magnitude. And those are images up to 2 minutes in length. So what we've got on the graph here is everything with a blue dot is our 2-second exposure images. Everything with a red dot is 10 seconds. Everything with a green dot is 30 seconds. So we were looking at different parts of the sky when we took these images just to get a good spread of what we could see. So the range of wavelengths we were collecting plus the exposure time in seconds is that graph, is that part, the information down at the lower right. Dimmer stars off to the right, brighter stars off to the left. Less accurate measurements near the top of the graph, more accurate measurements down at the bottom of the graph, and you can see that by seeing the spread of error bars that are on here. You can see very few error bars down, or very small error down here, much larger error, especially when you get to the dimmer stuff, and occasionally when you get to some of the longer exposures, at least in the case of that particular star right there, for whatever reason, that one was a high amount of error. And so the accuracy that we can get is really good. In many cases, we can get less than 1% error. Yes?
So the green is 30 seconds.
Green is 30 seconds, yes.
And it doesn't appear to go to the right as far as, say, the red one.
And it also depended on what part of the sky we were looking at and the sky conditions, but the longer we look, and so we were able to see some stuff down in the lower brightnesses. However, much more error. So that stuff was probably a little farther over in terms of brightness. So it depended on what part of the sky we were looking at as well. So longer exposure time and brighter stars, less than 1% error. So that's really good. And shorter exposure time, dimmer stars, less accuracy, about a 10% error. So the dimmest objects that we can get good, reliable data is somewhere in the 11th to 16th magnitude, taking 30-second images or less, maybe about 10 to 30 seconds or so. So that's our sweet spot. We can take up to 2-minute images, but anything more than that, we're not really gaining anything because the individual images, the light pollution is bad, and so we're not really going to get much dimmer than that in terms of these single images and being able to get those sorts of data. So what do we do with it? Well, we calibrate it. So here's one of our raw images, doesn't look like much. So you calibrate it and you take into account, if you know your astrophotography, bias, darks, flats. All right, so bias shows you the readout noise of the camera. The darks corrects the light images for thermal noise in the camera. The flats are used to correct some of your bad pixels, which you always have bad pixels, dust on the camera, dust on the telescope. And so we compare our images to existing database images, making sure we're looking at the right star. The photometry is we're determining the exact time the images were taken, the amount of energy given off by whatever we're looking at, and whatever we're comparing it to. If we see some sort of a change in our target and we have a comparison star in the view as well. Make sure that we don't see the same change in the comparison. You have a check star in your image as well to make sure that anything happening in the field of view, a passing cloud, a sudden brightness of some sort, you compare it to your check star to make sure that what you see, the change that you see in your target is actually in your target and not due to some other change in the image or in the sky conditions while you were taking that picture. So, proof of concept. Yes, it gets cold down there. We took our first variable star set of data in February, a couple years ago. And so I'm pointing at the star that we were looking at. So this particular kind of variable star is called a delta Scuti type variable star. It changes brightness over the course, this type of star changes its brightness pretty quickly. This particular one, over the course of an hour and a half. So this isn't several days worth of imagery. This is about an hour and a half worth of imagery, and it goes through one complete cycle of changing its brightness. And so this is the data we got. So we were looking at a star that was right in our sweet spot, about 14.5 magnitude. And this is our check star to make sure that whatever was happening in the sky was due to the sky and not the actual object. This is our comparison star. This is the one that already has a known brightness, and that we know that one doesn't change. And so any change that we see is due to the actual brightness change of the object. And so 80 minutes for this one to go through one complete cycle of changing its brightness, which is really, really great when you're taking data with students, because they're not always available multi-nights in a row. So getting this kind of data was a great proof of concept for us. And when we compare our data to prior data that other people have taken of the same star, we have even better accuracy with our measurements. So the green is our data, the red is existing data in an online database. What's also fascinating, we have less error and our telescope is smaller than the one that took the red data. So proof of concept, the M101 supernova that was visible a couple years ago. We wanted to see, could we see it at all? We didn't take data, we just took a couple images. So that is the supernova right there. Here it is right here. And you can see one of the reasons why you need to do some image, play with your image a little bit, clean it up a little bit, and take those flats. Yes, we have dust on the telescope, and whatever. Yes.
No, it's a UAP.
Yeah.
UAP.
UAP. Thanks, Tony. Right. And they're all donut shaped, right? Yeah, they're all donut shaped.
The alien spacecraft come in all shapes.
Right. Well, one of them is about to be bowling ball shaped. You know about Cosmos 482, right? Yeah, it's not really an alien, but you never know. I had to actually tell WGN Radio today, if anybody because they're like, well, what if it comes down? Don't touch it. Take photos. I want to see this thing. Anyway, sorry, I digress. So the next one, a proof of concept, exoplanet transit. So this was an exoplanet transit that we only got we got the last half of. And we were actually really amazed that we got this at all. So this is a star where the planet passes in front of it and has slightly under 1% brightness change. So pretty amazing that we can actually get this. So a 0.9% change in brightness for an 11th magnitude star. Pretty proud of that one. This one was a star that was about 14.5 magnitude, a 1.5% change in brightness. We think some of this was a little bit messy data there at the end, but you can see that very clear telltale dip in brightness. And this is, we reran the data, I think it's the same one, yeah. So this one we reran the data using a different program to be able to do it, different algorithm. And so we got a much better, much cleaner line for this particular set. Pretty proud of this. And here is what the dip looks like for professional data. So theirs is just a smaller graph. This is the professional data. This is data that our interns took last summer. And you can see it's pretty messy. This is a 16th magnitude star taken in the middle of summer in Chicago when it's very humid out. And so the fact that they got this at all is kind of amazing. So this was sort of testing the limits of what we were able to do. Now, the exoplanets that we think we can provide the most input on in terms of taking data and it would help the astronomical community would be any of those exoplanets and exoplanet transits that the TESS spacecraft looks at. Because TESS, if you're familiar with TESS, if you're not familiar with TESS, TESS looks at a wide piece of sky for about 30 days, and it then looks at another piece of sky right next door for another 30 days, and it keeps doing that, and eventually it'll cover most of the entire sky in its field of view. And the portion of the sky marked in red up here has almost continuous coverage by TESS and also the Webb Space Telescope right in that little dotted line right there. And so TESS has been looking at bright stars. So TESS primarily looks at stars that are brighter than magnitude 12. So it definitely is finding others but that are dimmer, but we think TESS's sweet spot is ours as well. And so there's a lot of TESS candidates. So they're looking for data where they need to prove that these really are exoplanets. So just seeing a few of these transits isn't quite enough. You need follow-up information, and you need continuous coverage of these exoplanet transits, because once TESS is done looking at those parts of the sky, it's going to move on. You can't keep focusing on the same spots, especially with the big telescopes, the ground-based telescopes. They've got too much to do. They have to move on to whatever their next research project is. We can point ours at whatever we want. And so we think these TESS exoplanets are going to be really great for helping the astronomical community to gather up a bunch of data about their exoplanets. Right now, TESS has 620 confirmed planets and over 7,000 candidates. So there's a lot of work to do to be able to follow up on as much of these as possible. Our interns last year took imagery of an asteroid and created what is called a light curve. So from a light curve, you can learn information about what the rotation of the asteroid is like. You can kind of get a sense of, is it round, is it oblong, what's the general shape of it. So they looked at asteroid Electra. Its rotation period is fairly short, so that is actually doable in at least part of the light curve might be doable in one night's imaging run. And it goes around the sun in between Mars and Jupiter. And that's their light curve, done by undergrads who took the data, processed it, and came up with the graph. They did a really, really nice job. And the fact that you can see that the light curve is stretched out longer here than it is here tells us that the asteroid is probably oblong in shape. So it's rotating kind of like this. So we've done a lot of imagery. We've at least got our characterization done. We've tried a variable star. We've at least taken pictures of a supernova. One of these days, if there's one that's bright enough, hopefully we can take some actual data on a supernova. We've got the exoplanet transit data. Asteroid imaging partly done. Mainly we did the light curve. Now we want to do color imagery to get a sense of what color is an asteroid. You take imagery in the different filters that we've got and see where it's brightest. And so we can get a sense of what the surface color would be for an asteroid. That's another set of information we'd like to get, hopefully this summer if we can. And then imagery of Jupiter over time, one of these days. It's not going anywhere. We'll do that at some point. And we want to submit the data to databases. We want to track change over time for some of these objects. That is important work that the big observatories can't do. And because we are taking data that others might be able to use as well, we're finding that there are some astronomy class professors, such as Joe Del Santo at College of DuPage and his astronomy class. We've given some of his students some of our data and say, here, play around with it, go for it, and try it out. So we love having sets of data that we can give out to instructors if they want to use our data in their classes. So these are our interns from last summer, and so we're going to have 2 more interns this summer, and they're going to start with us June 30th, so we're very excited about that. And because I can't talk all about the observatory and not show you pretty pictures too, I do have as the final set, we've got a picture of the moon with the greatest smiley face crater you have ever seen in your life. Is that not the greatest? I show that picture to the public and they're like, oh my God, look, it's a smiley face. They pick that out every single time. That is Maurolycus crater. It's about 70 miles wide. But the smallest features that we can see in an image like this are somewhere around a half mile to a mile wide. So pretty good, I would say. Jupiter through the telescope. These are single mainly unprocessed images, just taking quick snaps. The most I would do to these is just crop them so that it makes them look a little bigger. I stretch them out a little bit. But here you can see a Jovian moon shadow transit right here, and the great red spot is right there. But Jupiter looks spectacular through the telescope. I didn't mess around with the color with these. I didn't have the color quite right for these compared to what you see with your eye, but I just left the pictures the way they were. Saturn through the telescope looks, again, spectacular. This is Uranus, and I'm kicking myself that I haven't yet done this with Neptune, and I'm going to, but Uranus, because people want to see the dot, but then if you defocus it, you can see the color better. And so I've got Uranus and defocused Uranus, so that green, that light blue green color shows up really well. I want to do this with Neptune. I haven't done it yet. Especially since in the last year or so, they went back to the Voyager data and went, oh, they color enhanced Neptune in the pictures. We've all been thinking that Neptune is a lot darker blue than it really is. Neptune and Uranus are basically the same color. Which if you've seen them both through a telescope, you go, yeah, they are the same color. But I kept thinking to myself, oh, maybe I'm just not seeing it right. Nope, it always was the same color. M13, of course, through the telescope in the summer is just spectacular. And you just get that, one of those perfectly dry nights and just nice calm winds. There's nothing like it to see M13 through the telescope. We love defocusing stars to show people the color. So we've got Betelgeuse, Capella, and Rigel. So that shows the star color really, really nicely. One single snap, shows up on my screen a little bit better, but one single snap of the Orion Nebula unprocessed image. This is processed, so this is M51 from the observatory, which is really, really nice. And M87 I will leave you with, including the jet, the black hole jet right there. So it's a pretty cool place to work. Pretty cool that I've gotten the chance to change out the telescope and really come up with ways to use this where the administration has been just really, really supportive all along the way. So We're going to get a new president in the next few months. So they're searching for our new president right now. So I'm excited to work with whoever that is. And I would love to know if anyone has any questions about the Adler, the observatory, anything at all.